When you're learning about statistics, an important concept to understand is the difference between a one-tailed test and a two-tailed test. A one-tailed statistical test versus a two-tailed statistical test. So far we've been working with a two-tailed statistical test, and here the critical region is split onto both sides of the sampling distribution. All right, so we'll just work with the familiar scenario that we've worked with in the past. So our research hypothesis is that SUU men are taller than American men. So the corresponding null hypothesis we've had there is mu SUU, the average height of SUU men is the same as the average height of American men. And then the alternative hypothesis in that case is that they're unequal. Given this scenario, this here is the population distribution of American men's height if the null hypothesis is true. Right, so we recall that the mean of American men's height is 70 inches. The standard deviation of American men's height is 4 inches. So the mean of 70, standard deviation of 4. And this is the sampling distribution if the null hypothesis is true, and that'll be true for both of these. I'll illustrate the two-tailed test over here and the one-tailed test over here. We're going to start with the two-tailed test. So this is the sampling distribution. If the null hypothesis is true, remember this is expected sample means. These are the kind of sample means you expect to observe if the null hypothesis is true, and that's where you're getting your samples. So the mean of that distribution is going to be the same as the mean of the distribution where the samples came from. The standard error is the standard deviation divided by the square root of the sample size, and so this is going to be our observed sample. And if our observed sample has a sample size of 100, then 4 divided by 10, 0.4. Okay, so up to this point, the one-tailed and two-tailed tests are actually the same, so I'm just going to redraw the same information over here. Because the one-tailed test versus the two-tailed test doesn't influence what these distributions are like. And we got our sample distribution. With the two-tailed test, we have a alpha of 0.05, and just like in the past, we would put half of that on either side. And so this alpha of 0.05 is split between these two tails. And that's what makes it a two-tailed test. For comparison, let's talk about the one-tailed test. So I'm going to create a little bit more space here to write. In a one-tailed test, the critical region is on the side of the sampling distribution expected by the research hypothesis. In fact, so these hypotheses end up being drawn up a little bit differently for a one-tailed test. So the research hypothesis is the same, so I'll put these down here. So we got the research hypothesis is that SUU men are taller than, let's say, than American men. So for one-tailed test, I'm actually going to write the alternative hypothesis first. So it just says that the height of SUU men is taller than the height of American men. And then the null hypothesis is whatever is required to finish off all possible states of the world other than this. So if they're equal or SUU men are shorter. All right. So our research hypothesis is the same, but our null and our alternative hypotheses end up being a little bit different. Two-tailed test, you say the null hypothesis is they're exactly the same as each other. For a one-tailed test, the null hypothesis says that SUU men are the same or shorter. So when you're doing the one-tailed test, we're going to keep alpha the same. Alpha is still going to be 0.05, right? Remember, this is our false positive rate, the rate at which we reject the null hypothesis when we shouldn't. But now, all 5% are going to be on one side. And the side is the one expected by the research hypothesis, or equivalently the alternative hypothesis, right? So it's SU men being taller. So taller heights are over this way. And so what we're hoping to find, right, is that our sample is going to be so tall that it's not the kind of sample that you expect if this is where we're getting our sample. And if it's tall enough, we're going to reject the null hypothesis. All right, so we've drawn the critical regions for a two-tailed test or one-tailed test, with everything else being the same in this case. The next thing I want to do is calculate the critical values for these two different scenarios. Remember, that's the z-score, the z-statistic. That is the threshold where a z-statistic for our sample mean. Beyond that, we will reject the null hypothesis. And we need the z-critical here for there to be 0.025 beyond it. And so if you look in your z-table, you'll find that it's 1.96 over here, z 1.96, or on this side, negative 1.96. So it's plus or minus 1.96. So any observed sample that is 1.96 standard deviations above the mean or below the mean will reject the null hypothesis using a two-tailed test. For the one-tailed test, what we need to do instead is find the z-score, the z-statistic, with 0.05 beyond it, and that is 1.64. So here, a sample mean only has to be 1.64 standard deviations above the mean on this distribution for us to reject the null hypothesis. But it doesn't matter how short the sample is. If we use a one-tailed test, we would never reject the null hypothesis for a shorter sample than what we were looking for. So our z-critical here is 1.64. It's not plus or minus like it is here. That indicates a two-tailed test. It's just plus 1.64 for the one-tailed test. So the first example I want to do, we'll call, so it'll be mean 1. We'll say the SUU men's height is 70.80. We'll say the standard deviation is 4.2. Doesn't actually matter too much for us. So now what we can do is we've got our sample mean, and we can calculate the z-statistic of this score on these two distributions. So z-statistic equals the sample mean minus the mean of the sampling distribution, divided by the standard deviation of the sampling distribution, the standard error. So we got 70.80 minus 70 divided by 0.4. So this is going to give us a z-statistic of 2. Notice the z-statistic of 2 is the same on this distribution and this one because the means and the standard deviations of these two distributions are the same. So the sample mean has a z-statistic of 2 regardless of which distribution you're on. So let's consider the two-tailed test for a second. With a z of 2, that's going to be over about here. That's going to fall in the critical region because it's more extreme than our z critical of plus 1.96, and we're going to reject the null hypothesis. And now if we look at the one-tailed test, a z of 2 is also in the critical region. It's beyond the z critical, and we're going to reject the null hypothesis. So if our sample data is 70.80, it doesn't matter which test we're going to use. We're going to end up having the same decision either way. All right, so now we're going to do another example. Here the sample mean we'll say is 70.72. Again, we're going to calculate the z-statistic for this different sample mean. So our z-statistic is 70.72 minus 70 divided by 0.4. And this is going to give us a z-statistic of 1.8. So our sample mean is 1.8 standard deviations above the mean on this distribution, or equivalently on this distribution. Now if our sample mean has got a z-statistic of 1.8 on this distribution, that would put us about right there, and that is not in the critical region. This z-statistic is not more extreme than our z-critical. We're going to fail to reject the null hypothesis. We're going to decide our results are inconclusive, and we're going to say, well, we don't know if SEU men are taller than American men. That's with the two-tailed test. If we did the one-tailed test and we got a z-statistic of 1.8, that's going to be over here. That's more extreme than our z-critical. It falls in our critical region, and we're going to be able to reject the null hypothesis, and we're going to say, hey, given our results, we think that SEU men are taller than American men. So with this kind of a sample, you end up getting a different decision depending on if you have a one-tailed or a two-tailed test. And in this case, you're better off having the one-tailed test because you're able to reject the null hypothesis, which is what you're hoping to do. All right, we'll consider a third scenario here. A third sample mean that is, we'll say 70.40 inches tall. So we'll calculate our z-statistic. 70.40 minus 70 divided by 0.4. So here our z-statistic is going to be 1. With a z-statistic of 1, with a two-tailed test, our sample mean will be right about there. It's not in the critical region. It's not more extreme than our z-criticals equivalently, and so we're going to fail to reject the null hypothesis. And if we did a one-tailed test with a z-statistic of 1, the same result happens. Our sample mean isn't in the critical region. It's not, our z-statistic's not more extreme than our z-critical, so we fail to reject the null hypothesis. So in that case, you get the same decision regardless of how you did it. One-tailed test or a two-tailed test. And then the final scenario I want to go through, we'll say that the observed sample mean is 69.20. As usual, we'll calculate our test statistic, our z-statistic in this case, sample mean minus the sampling distribution mean divided by this standard error. And now we're going to get a negative 2. So our z-statistic now is -2. So we're over on this side of the distribution, right around here. So with a two-tailed test, we found a sample that's unusually short if this is true. And so much so that we're able to reject the null hypothesis. And in this case, we would decide that SUU students are in fact shorter than American men. If we did a one-tailed test and we got a z-score of -2, that's not in the critical region. It's not more extreme than the z-critical value, and so we're going to fail to reject the null hypothesis. And this is really where the big difference lies between these two tests, is that the two-tailed test is sensitive to observed samples that are in the opposite direction from your research hypothesis. And the one-tailed test is only sensitive to data that's consistent with it. In practice, researchers are almost always interested when the research hypothesis is not only wrong, but the world is actually the opposite of what they expect. So let's say you do a study where you give some participants caffeinated coffee, other participants decaffeinated coffee. You think the caffeine group is going to be more alert than the decaf group. If it turns out that caffeine actually decreases alertness, as a researcher, you'd really want to know that. And when you're doing your statistical test, you could only detect that kind of an effect if you use a two-tailed test. A one-tailed test wouldn't tell you that. So whenever you're actually doing research, you always want to use a two-tailed test, unless you literally don't care at all if your research hypothesis is not only wrong, but it's wrong such that the world is actually the opposite of what you expected. And in practice, researchers are almost always interested to find out the world is opposite of what their research hypothesis expected, because when that's the case, that usually means that they really need to reconsider the whole theory that they're using for their research. And there's another problem with using a one-tailed test. And it's a problem that comes about just because of kind of human nature. So let's say I'm a researcher and I'm doing my test about SU men's heights. And I've decided, I want to do a one-tailed test because I think SU men are going to be taller. So I put all my data into SPSS, I run the analyses, and I find out that SU men, if anything, are shorter than regular American men rather than taller. I say, whoa, that's really interesting. You know what? Now that I see the SU men are shorter, I'm actually going to just switch this from a positive to a negative one-tailed test. Now, if you do that, and that's a temptation that you might have, if you do that, then your alpha is actually not 0.05 anymore. It was when you did just that first test, but now you're allowing the 0.05 to show up on either side. Because you were interested, you would have rejected the null hypothesis if it were above, but now that it's below, you're also willing to reject the null hypothesis. So now what you've done is you got 0.05 over here, 0.05 over here. The alpha you're actually working with is 0.10. You maybe didn't realize that you've switched, but you have. And so that's a risk, a temptation of working with one-tailed tests. So again, generally, when you're doing research, you always want to use a two-tailed test unless you literally don't care if your research hypothesis, if the world is opposite of what your research hypothesis expects it to be.